What's up everyone and welcome back to the channel. Today we will discuss a very foundation of building a massive AI model which we call the pre-training phase. But before we can train the model, we have to teach it how to read. You might think we just feed these models whole words, right? Actually doing that would completely break the system. If you feed an AI whole words, it fails the second it sees a typo, or when reading a language like Thai that doesn't use spaces between words. So why not just feed it letter by letter? Because the computing time for a transformer model grows quadratically with the length of a sequence, if we did that, processing time would absolutely skyrocket. So the brilliant solution is something called a tokenizer. To fix this sequence length problem, researchers use algorithms like Byte pair encoding or BPE, which is one of the most commonly used tokenizers. It starts by taking a massive corpus of text and assign a unique token ID to every individual character. Then it scans the text and iteratively merges the most frequent pairs of characters together into a new single token. For example, it might see the letter T and O next to each other frequently, so it merges them into a single token called TO. Over time, it builds up common chunks, usually averaging about 3 to 4 letters long. For instance, a tokenizer doesn't read the word tokenizer as a whole word. It usually splits it into two distinct tokens, tokenizer. It is very important to know that these tokenizers don't understand meaning. They just assign IDs. If you write the word bank for money and bank for a river, the tokenizers give them the exact same token ID. It's up to the neural network to learn the context based on the surrounding words later. By building these chunks, the model efficiently reads most of a sentence. But crucially, the tokenizer still keeps all those original individual character tokens in its vocabulary. That way, if it sees a weird typo, it doesn't crash. It just falls back to spelling it out character by character. But you have to understand that this system is not perfect. It's actually why AI sometimes struggle with maths. Because it chunks common things together, it might just read the word 2, 3, 4 as one single token instead of the individual digits 2, 3, and 4, making it hard for the AI to do composition and arithmetic the way humans do. Once the AI knows how to read these tokens, it starts its primary task, which is playing the world's most advanced game of autocomplete. But how does an AI actually predict the future mathematically? It uses something called an autoregressive language model. Instead of a magical thinking brain, an AI is essentially calculating a massive probability distribution over a sequence of these tokens. Imagine the AI is holding a giant menu containing every single token in its vocabulary. When you feed it a sequence of words, for example, the mouse ate the AI runs the math and assigns a percentage to every possible next token. Because its goal is to model how humans naturally speak online, it applies syntactic and semantic knowledge. It might give the word cheese a very high probability, but it knows that the mouse is semantically weird. So it would give mouse a very low probability. To write a full sentence, it just relies on something called the chain rule of probability. It predicts the first word, then multiplies by the probability of the second word given the first word, and loops that process over and over. But to learn these very precise mathematical percentages, it has to read a mind-boggling amount of text. So the engineers use web crawlers to download around 250 billion web pages, which is roughly around 1 petabyte or even more, or millions of gigabytes of data. To put 1 petabyte in perspective, it's roughly equivalent to storing a continuous HD video playing 24/7 for over 3 straight years. But the raw internet is not very clean. It's an absolute mess of broken HTML, toxic comments, and endless duplicated text. So to turn that raw dump data into a usable dataset, engineers have to build a very rigorous, massive filtering pipeline. First is the extraction. You have to rip the actual text out of the HTML formatting while carefully trying to save complex information like maths equations. Second is filtering undesirable content. So people use extensive blacklists or small classification models to scrub out toxic content, harmful material, or personally identifiable information. Third is deduplication. This step is very critical. The internet is full of repetitive boilerplates like forum footers or famous book passages copied tens of thousands of times. If you don't remove these, the AI will essentially just memorize them instead of learning general language rules. Fourth is heuristic filtering. Developers write strict rules to throw out obvious junk. For example, if a website only has 3 words on it, or the average word length is absurdly long, or if the distribution of tokens is a massive outlier, the entire page gets tossed out. The fifth step is model-based filtering. Finally, these developers and engineers train a small AI classifier to identify high-quality data, like paper references, for example. And they intentionally upweight web pages that match that high-quality style. They also try to upweight domains like coding, which helps the model learn general reasoning skills. So before a single gradient update even runs on the AI, a massive amount of engineering has already happened just to make the training data usable. But once you have all of this clean data set, how do these researchers and developers know exactly how big to build their neural network without wasting tens of millions of dollars? So in our next video, we are going to look at what we call the scaling laws. Subscribe to catch the next one, and I will see you in my next video.